All right, and away we go on the last podcast of week number 9. This is podcast number 4. Same analysis of Le Chatelet's principle. That is the theme of this entire week. And we are moving on to the next possible way that we can cause a stress on an equilibrium. And that is with a change in pressure, which of course in turn causes a change in volume or vice versa. You explored the relationship between pressure and volume quite a bit in Chemistry 20. Now that being said, probably haven't thought about it too much, so I will remind you. Now ultimately what happens is when you compress a container, and compressing by its nature is increasing the pressure, right? You're compressing, you're pushing down. Notice we have an inverse relationship here between pressure and volume. Going back to Chem 20, that's according to Boyle's law. Anyway, a decrease in volume is what I mean by it being an inverse relationship. When one increases, the other decreases. And you have to keep that in your head to make sense. Now, it's pretty logical. Let's just say you take a syringe or something, like, I don't know, the ones you play with. I don't know. Honestly, my kids would play with them at the bathtub or something, right? But take a syringe, stopper the end, and then push down on it so that the air inside compresses, right? So what happens? Well, you're pushing pressure by pushing down on the stopper, and the volume is going down. Increased pressure, decreased volume. This is not new. Same thing would apply for, say, an oxygen tank when you're going scuba diving. Those tanks are under incredible pressure. Why? So that you can push a whole bunch of oxygen gas into a smaller amount of volume. Increased pressure, decreased volume. Anyway, ultimately then, you compress something, you decrease the volume. Vice versa, if you do the opposite, which would be expansion, then you are increasing the volume, right? You're letting it flow out, be free-flowing. That will decrease the pressure. Inverse still remains. More volume means less pressure. Keep those in the back of your head. That is a big deal because we're going to focus on how that idea relates specifically to an equilibrium equation. Now, ultimately, this all relates to the amount of reactants or products. Now, by amount, think back to what amount means from a chemistry perspective. We're not talking about mass, grams. No, amount is always in reference to the number of moles. And moles indirectly relate to mass, sure, right? Moles is equal to mass over molar mass, but it's not a direct relationship. 1 mole is not 1 gram. Not even close. Mole represents a certain number of particles. 1 mole is 6.02 times 10 to the 23 particles, right? That's a massive number. So it's a different entity than mass. Now, if we're focused on the number of reactant particles and the number of product particles, that's why we talk about moles. Why? Because the fewer particles you have, the easier it is to fit them into a compressed space. And vice versa, if you have a bigger volume, a bigger space, why not have more particles present? How do you compare amounts? Like I said, focus on moles. But ultimately what this comes down to is if you increase the pressure, naturally the volume's going to go down. So that means we're going to want to have the reaction favored that produces fewer particles. This is specific to gases, guys. Anytime we're dealing with an equilibrium situation where we're focused on a change in volume and pressure, it'll be about gaseous reactants and products. All right, vice versa, what if we decrease the pressure? If we decrease pressure, we in turn are going to increase the volume, which means that it's no problem at all for there to be more gas particles, right? So it's all about keeping in mind that inverse relationship between pressure and volume. Ultimately, the whole purpose of equilibrium shifts is to always oppose the change, to do opposite of the change. Okay, here's our equilibrium system that we'll examine, the formation of ammonia gas. And just looking at this right at the beginning, I want you to recognize that we have a total on the reactant side of 4 moles present. 1 mole of nitrogen gas and 3 moles of hydrogen gas. Vice versa, on the product side here, we have a total of 2 moles of ammonia gas. 2 moles would take up less space than 4 moles. They would be easier to fit into a smaller area. Keep this in the back of your mind as we continue. Here's your example. We're going to compress a system to a smaller volume. So again, use that inverse relationship to make sense of this. If we are decreasing volume, that means that we are increasing pressure. So naturally, if it's a smaller space, smaller volume that you're dealing with, you're going to want to have the fewer number of particles. That means we're going to favor the forwards reaction. We are favoring our ammonia because there's only 2 moles there. Okay, here's one thing that's new though. When you do these and you compress it, the first thing that's going to happen is all of a sudden you have a certain number of moles in a smaller volume, right? So think about this relationship. N over V equals C. And we are going to suddenly decrease the volume. Well, concentration and volume are inversely related. So if I decrease volume, concentration goes up momentarily until I can get the equilibrium to shift and get a new resulting one. But ultimately, because I'm suddenly decreasing the volume like that, every single one of these gases is going to have a sudden increase in concentration, right? And that's what's measured on this y-axis. Again, why? Because you decrease the volume. It's an inverse relationship. Therefore, suddenly you have the same number of particles in a smaller space. Thus, concentration goes up. Now, we will shift to the smaller number of particles, which means I'm going to increase my amount of my NH3, okay? In terms of how that is going to increase, we're going to see it go up by a factor of 2. And then it'll flatten out nicely there, okay? Keep on going. My H2 gas, vice versa, is going to go down. Why? Because it's reacting to shift to the products. But it's going to go down by a factor of 3 because we have a whoopsies, that's not what I want. Come on. There we go. Because it's got 3 moles. Vice versa, our N2 gas is going to shift downwards now by a factor of 1. And again, I know it's hard to properly draw a 1 shift, a 2 shift, so just make a little note. This is going down by a factor of 1. This is going to go down by a factor of 3. This is going to go up by a factor of 2. Therefore, if your drawings don't show that quite perfectly at all, then you can still have a way to communicate it, if you will. Okay? Key thing, though, is we have that sudden increase in concentration followed by the shift to the fewer number of particles. Let's do another one. What if we expand the system to a larger volume? Well, similar type thought process. Concentration is equal to number of moles over volume. So if all of a sudden I increase volume, inverse relationship, concentration is going to go down, and it goes down for all 3. So keep that in mind. That increased volume goes with a decrease of pressure, which means suddenly I've got room for more molecules. In other words, I can shift to the reverse reaction, to the nitrogen gas increasing and the hydrogen gas increasing. But first, the concentration of all 3 is going to go down because I expanded the system. So show that sudden decrease for all of them. Now we'll get to the shift. Remember, we're shifting to make more particles. So the N2 gas is going to shift upwards until it balances out at equilibrium. The H2 gas is going to shift upwards by a factor of 3. There we go, until it can balance out. And the NH3 gas, the ammonia gas, is going to shift down. Technically not to 0. It just kind of looks like it with the drawing. And then it balances out. Again, please write in, this is a ×2 shift. My H2 gas is going to be a ×3 shift, and the N2 gas is going to be a ×1 shift. There you have it. Do not though forget to show that sudden decrease when this system was expanded, vice versa the sudden increase in concentration here when the system was compressed. Now take note, pressure and volume changes like these have absolutely no impact on the value of Kc because equilibrium will naturally go back to its balanced state again in the end, right? We're not inducing a temperature change here causing a permanent shift to the forwards or to the reverse reaction. Now, a couple other scenarios that I just want to talk about, especially when it comes to gases. Here's one of them. What if the total amount of these reactants and products is identical? So in this scenario, when you make hydrogen iodide gas, we've looked at this equilibrium system before. We have 2 moles in total reacting, and we have 2 moles of gas in total being produced. So there's absolutely no advantage to shifting to the reverse or shifting to the forwards reaction from a pressure volume perspective. It's useless. This is one of those circumstances then where honestly an equilibrium shift won't occur. However, you still have to pay attention to this. We expand the system to a larger volume. So volume goes up. In other words, pressure goes down. There is no advantage to shift to the reverse or the forwards reaction. But concentration is still impacted initially by that change in volume. Volume goes up, therefore concentration goes down. So we will see initially a noticeable drop in all 3 gases' concentrations. Once that noticeable drop has happened, there is no shift. It just stays. Okay, come on, draw a straight line. There we go. Okay, we don't have a shifting equilibrium because there is nothing useful about the shifting in terms of opposing the change. So it just stays constant. Okay? One more scenario as it relates to gases before we're done. What if you add something like an inert gas? By definition, an inert gas doesn't react. We're looking at those group 18 gases, stuff like helium, neon, etc. Okay? Now, what if we add it to a flask specifically? And we're going to stop with the flask. Ultimately, we have a scenario where we're not going to allow volume to change. Oh, this gets interesting. Now, you are still, though, going to impact pressure. Oh, so think about this. We are affecting pressure because you're adding more gases. So essentially, you're making the net pressure different. The partial pressure of each gas can remain the same, but the net pressure has increased. And yet, the concentration doesn't change. Okay, I'm going to imagine, just to kind of explain this, let's say our flask is just a 3D block container. I knew I'd draw it or two-dimensional, but whatever, you get the idea. And let's go back to our hydrogen and iodine gases reacting to form hydrogen iodide. I'm going to call my hydrogen gas, the H2 gas, is going to be a blue dot. And let's say I have 1, 2, 3, 4, 5, 6, the equivalent of 6 moles of gas in this container. And then I'm going to call my iodine gas in this particular drawing a green dot. So I have 1, 2, 3, 4 moles, say, of that one in there. And then I'm going to make my hydrogen iodide gas that I have in there red. And I'm going to have 3 moles of the red ones. There I've got my different concentrations of each one. Well, if I come along and I add an inert gas and we add helium. Helium is another dot. And I'm going to add 1, 2, 3, 4, 5 moles of it. Look what happened. I still have the exact same numbers of moles of hydrogen in the same volume. Hence, concentration is the same. I still have the exact same number of iodine moles in the same volume. Concentration is the same. Exact same number of hydrogen iodide moles in the same volume. concentration is the same. So even though I added an inert gas, which impacted the overall pressure because I had more particles pushing and forcing against each other in a closed space, it did not affect the equilibrium. It does not shift it. So the message is, adding an inert gas, though it will increase the total pressure, it does not affect the partial pressures. Therefore, absolutely no equilibrium shift. None, nada, nothing. How would you show this on our previous equilibrium system? So imagine that we're adding that inert gas, that helium. Honestly, guys, you do not affect concentration. You do not shift to the equilibrium. Therefore, no change, and no change. It will not shift. Same. Okay? Now, reactions in general can be sped up or slowed down by a catalyst. And we've talked about catalysts before, especially in the context of our first unit, where we recognize catalysts can decrease the activation energy necessary for a reaction to proceed. So even though catalysts speed up or slow it down, once you hit the equilibrium, the reaction is still set. So that's established regardless of if you reach it at a faster rate or a slower rate. Therefore, guys, a catalyst does not affect the equilibrium constant in any way. It simply will help you to reach equilibrium faster or slower. Okay? So to recap, concentration, no effect on an equilibrium constant. Okay? Pressure, temperature, no impact on an equilibrium constant. Catalyst, no impact on an equilibrium constant. However, big deal, temperature, yes, this will affect the equilibrium constant. It will change it. If you are favoring the products, you will increase the value of the equilibrium constant. If you are favoring the reactants, the reverse reaction, you will decrease the value of the equilibrium constant. Dun, 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 dun. That is the end of our week 9 podcasts. You can now finish the remainder of your assignment. Do all of number 2. You haven't had to do any of that one yet. Hint, you are going to have to figure out what the enthalpy change is for number 2 before you can proceed with predicting the shift or the temperature change. And you can also finish 3E, which is going to relate to pressure or temperature differences being stressed on an equilibrium situation. Good luck, guys. We will do that Google Meet 11 o'clock on Thursday. So feel free to come in and ask questions then. Otherwise, you can address them to me individually. Take care all. Bye-bye.